The creation of the largest map of the universe using data from the James Webb Space Telescope represents one of the most astonishing achievements in modern astronomy, offering humanity a breathtaking window into the structure, evolution, and ancient origins of the cosmos. This monumental map, unveiled by the Cosmic Evolution Survey collaboration, compresses an almost unimaginable amount of information into a tiny section of the sky, just 0.54 square degrees, an area equivalent to only about 3 times the size of the full moon as seen from Earth. Yet within this seemingly small patch lies a vast ocean of nearly 800,000 galaxies. Each of those galaxies contains hundreds of billions of stars, planets, nebulae, black holes, and countless cosmic mysteries, all packed into a visual archive that stretches across nearly the entire history of the universe. When we peer into the depths recorded in this map, we are not just looking across space. We are traveling across time, observing galaxies as they existed billions of years ago. Some formed only a few 100 million years after the Big Bang. To build this remarkable map, the James Webb Space Telescope spent 255 continuous hours staring at a region known as the cosmos field, a carefully chosen patch of sky famous for its clarity. Astronomers selected this region because it contains minimal interference from foreground stars, dust clouds, or bright objects within the Milky Way that might obstruct the view of the deeper universe. For nearly 2 decades, the cosmos field has been one of the most studied areas in astronomy, observed using a wide variety of telescopes across different wavelengths: radio, infrared, optical, ultraviolet, and X-ray. However, it was Webb's unmatched infrared sensitivity that allowed scientists to push deeper than ever before. By detecting faint, stretched-out light from the earliest galaxies, Webb has provided a level of detail, clarity, and depth that no previous telescope could achieve. Because the universe has been expanding for more than 13.8 billion years, the light emitted by ancient galaxies does not travel to us unchanged. As space expands, the wavelengths of the photons traveling through it stretch, shifting from the visible range into the infrared. This phenomenon, known as redshift, means that light which once would have been visible to early cosmic observers is now detectable only with advanced infrared technology. This is why the James Webb Space Telescope was designed from the beginning not as a traditional visible light observatory, but as a highly specialized, extremely sensitive infrared machine. Its purpose was to look back far enough in time to capture the glow of the earliest stars and galaxies, light that has been traveling toward us for more than 13 billion years. The results have surpassed expectations. According to Caitlin Casey, a professor of physics at the University of California, Santa Barbara, and co-lead of the Cosmos Project, the data revealed something astonishing. Webb detected roughly 10 times more distant galaxies than predicted by existing cosmological models. This discovery has sparked significant excitement and debate within the scientific community. For years, astronomers assumed that galaxies in the early universe would be sparsely distributed and relatively small. Instead, Webb is showing that these ancient galaxies were far more numerous, brighter, and more massive than previously believed. Some appear to house supermassive black holes much earlier in cosmic history than current theories can easily explain. These findings have prompted scientists to revisit long-standing ideas about galaxy formation, star birth, and the growth of black holes during the universe's first few billion years. One of the most remarkable aspects of this newly compiled map is how accessible it now is. Although the raw data from Webb's Cosmos observations was released publicly soon after it was collected, the unprocessed files were extremely difficult for non-experts to use. Raw telescope data typically arrives as complex, uncalibrated images filled with distortions from the instruments, background noise, cosmic rays, and other interfering signals. Transforming this raw material into crisp, scientific-grade images requires a deep understanding of astronomical imaging techniques, access to powerful computing systems, and hundreds or even thousands of hours of processing work. The Cosmos collaboration spent 2 years meticulously cleaning, organizing, aligning, color mapping, and stitching together the data, converting a mountain of technical files into a polished map that can be explored easily by anyone with an internet connection. The scale of this project cannot be overstated. Each of the almost 800,000 galaxies within this map represents not just a dot of light, but a fully developed system containing its own history of star formation, gravitational interactions, and evolutionary changes. Some galaxies in the map are massive spirals similar to our Milky Way, while others are chaotic, irregular systems shaped by collisions and mergers in the early universe. The images include star-forming galaxies filled with glowing gas, compact red galaxies that have stopped forming stars, and even bright quasars powered by supermassive black holes. Some galaxies appear smooth and round, while others look like faint smudges, distorted shapes, or barely visible whispers of ancient light. The oldest galaxies captured in the map existed only a few 100 million years after the Big Bang, meaning their light has been traveling for more than 13.5 billion years before finally reaching the mirror of the James Webb Space Telescope. This map is more than a simple image. It is a scientific treasure chest. By studying the distribution of galaxies across this region, astronomers can better understand the large-scale structure of the universe, including how galaxies cluster, how dark matter is distributed, and how cosmic expansion has changed over time. The unprecedented number of detected galaxies allows researchers to look for rare objects, such as the earliest supermassive black holes or unusually bright star-forming regions, which could hold clues about how galaxies grew so quickly in the early universe. Additionally, the map includes galaxies at many different distances, effectively turning it into a time machine that records various eras of cosmic evolution. By analyzing patterns in these different stages, scientists hope to piece together a more complete understanding of how the universe transformed from a hot, dense cloud of particles into the complex web of galaxies we see today. For amateur astronomers, students, educators, and the general public, the release of this map is especially meaningful. For the first time, non-experts can explore the deepest regions of space in astonishing detail, zoom into galaxies that existed billions of years before Earth formed, and visualize the vastness of the cosmos at a scale that was previously accessible only to professional scientists. The interactive viewer created by the Cosmos team makes it possible to browse the map like a digital atlas of the universe. Users can zoom in on faint galaxies, compare structures across cosmic time, and witness firsthand the diversity of shapes, sizes, and colors that fill the universe. This level of access represents a major step toward democratizing astronomy, bringing cutting-edge scientific discoveries directly into the hands of the public. The James Webb Space Telescope, though launched only a few years ago, has already transformed our understanding of cosmic history. With its ability to observe the universe in infrared, its extraordinary mirror size, and its sophisticated instrument suite, Webb can see objects that are far too faint, distant, or ancient for any other telescope. Scientists had long speculated that Webb might challenge certain aspects of the standard cosmological model, but few expected the magnitude of the surprises it has delivered. The discovery of massive mature galaxies at unexpectedly early times, as well as unexpectedly bright black holes, has encouraged researchers to re-evaluate theories about how fast structures formed after the Big Bang. Some scientists have suggested that the early universe may have been more efficient at forming stars than previously believed, while others propose revisions to models of dark matter behavior or galaxy growth.